The mass transfer situation that we just did for multiple layers, we'll now see how to extend that to other geometries. So we did for a slab and we want to extend it for a cylinder and sphere. So we just did an example of multiple resistances in a slab geometry. This could happen, for example, in moisture transport through our body through various clothing layers. Likewise, there can be multiple resistances in a cylindrical geometry, like flow through dialysis tubes that we did earlier. Now, one confusion can be that we use the slab formula for the dialysis tube. Were we wrong? And no, we were not wrong, because we can show, and this has been done in heat transfer, the resistance in cylindrical coordinate in heat transfer when the material is very thin, as is the membrane in case of this dialysis problem that we did. When the material is very thin, the resistance of this cylindrical tube becomes the same as the resistance for a slab. So these tubes being very thin, we got away with the formula for a slab which were approximate for a cylinder. Otherwise, we can use we would have situations where we need to deal with a cylindrical geometry. Likewise, there can be multiple resistances in a spherical geometry. For example, drug diffusion through multiple layers of the drug coating. And so our goal would be, how do we get mass flow for these two situations, in a spherical geometry or in a cylindrical geometry? Now the processes in these coordinate systems are analogous. So we can go through the same steps, exact same steps, but in the respective geometry, cylindrical and spherical, and at the end, mass flow will be given by the same equation. That mass flow is concentration difference divided by the total mass transfer resistance of each, the resistances of each layer added together. Thus, this equation is really universal. This is not geometry dependent. We just have to use the corresponding resistance term for that coordinate system. Now notice, this is all true for steady state only.